Okay, so welcome to the third session for today. We already talked about what scalar variance is, what scalar dissipation rate is. By now you should know the scalar dissipation rate affects the evolution of scalar variance. Now, this is a topic very close to my heart because I have been working actively on this topic and still I'm working on it. So, I will start the discussion from the point of view of a reacting fluid. Obviously, for the sake of generalization, I'm starting for reacting fluid. If we don't have chemical reaction, the reaction terms go to zero. And then you get what we expected for non-reacting fluid. Let's say this is my active scalar, reaction progress variable, defined in terms of some kind of suitable species mass fraction. I have used subscript 0 to refer to the unburned reactant values and infinity to the fully burned product. So just to recapitulate, C takes a value of 0 in the unburned gas, 1 for the fully burned gas. Okay? These are the transport equations of C, instantaneous reaction progress variable. This is the reaction rate term. This is the molecular diffusivity of C, our active scalar. Okay. You can write this equation for any scalar. It doesn't need to be reaction progress variable. In the case of passive scalar, this term is essentially 0. Here, if I consider the transport equation of Fabry average reaction progress variable, I will take this form. For whatever reason it is not coming here, it is a row bar, obviously, because it is written in terms of the average. Now, in the context of Fabry averaging, variance can be actually approximated by this. It's not exactly equal to. In the context of Reynolds decomposition, it is exactly equal to, because if you replace tilde by bar, you'll get exactly equal to. In the case of Fabry averaging, is approximately equal to. So if you actually multiply this equation by C, you will get a transport equation for C square. If you multiply this equation by C tilde, you will get a transport equation for C tilde square. And then if you subtract them, you will end up with this equation, which is the transport equation for scalar variance. You have seen this equation, but now I am telling how to actually obtain that transport equation. Transient term, mean advection term. This one is turbulent transport term. This one term which you are sitting within the square bracket, this is the scalar flux of variance. As I told earlier, it does not generate or destroy, it redistributes. This one is often referred to as generation term, contribution of mean scalar gradient. As I told earlier, if you have gradient type of transport, it generates. If it is counter gradient transport, it actually kills. Okay? This is the reaction rate contribution. So if you are dealing with passive scalar, this term will go to 0. Clear? But in the context of reaction progress variable, it actually generates scalar variance. Because of the chemical reaction, it essentially gives rise to scalar variance. Happy so far? This is molecular diffusion of scalar variance. Again, molecular diffusion term does not generate or destroy, it just redistributes. And this one, I don't know whether it's captured in this slide. Green term is basically two row bar epsilon tilde. This is the scalar dissipation. If I consider this transport equation, and if you are solving this, you want to solve this transport equation in the context of advanced simulation, this is an unclosed term. Okay? in order to solve this equation, you already need this scalar flux. So this term is closed. This term is unclosed because mean reaction rate we talked about, this is an unclosed term. You need closure for this. Already you need closure for mean reaction rate, but now I have correlation between reaction rate and reaction progress variable. So I need a model for this one. Clear? And this is also an important unclosed term, the scalar distribution rate. Obviously, you can skip the modeling of this if you are dealing with non-reacting flow, because this term disappears, but you cannot get rid of this term. This term is there whether it is passive scalar or reactive scalar, always there. Although behavior will be different, but it is there. This closure is there. And you can't get rid of this one. So, as I said, T2 and T4 are closed, everything is unclosed. Now, let's consider that I am talking about a premixed flame. Premixed flame means reactants are homogeneously mixed prior to combustion process. This is what happens in spark ignition engines. Okay? Now, the region where the chemical reaction takes place is really, really thin region. So if this is my sampling location, I will see either, if you look at this broken line, I mean, I'm sampling around this broken line, and most of the time I'm going to see C equal to 0 or C equal to 1. This is the probability density function of reaction progress variable. If that is the case, this kind of PDF is called bimodal PDF, and that can be approximated by this. These are Dirac delta functions. So alpha is the weight given to this Dirac delta function, beta is the weight given to this Dirac delta function, and you have some variation in between. This is essentially the contribution coming from burning mixture, which is between C0 and C1. Why between C0 and C1? C0 means unburned reactants, no chemical reaction has started. C equal to 1 means all chemical reaction is finished, are finished, right? So now this contribution is generally extremely small or high values of Dampolan number. Dampolan number is a non-dimensional number given by large scale turbulent time scale, chemical time scale. So if I'm telling Dampolan number very high, that means you have very fast chemistry. Chemical time scale is very small. Okay? So in the context of fast chemistry, this contribution can be neglected. So that's why very often the third contribution is written like this. Varies us 1 for Dampolan. Higher the Dampolan number, lower. Generally, this kind of parameterization is valid when Dampolan number is much greater than. And based on that, one can come up with this kind of joint probability density function between velocity and reaction progress variable. Okay? Let me explain what PR and PP. PR is the probability density function of velocity in the unburned gas. PP is the probability density function of velocity conditional on fully burned product. Okay? And then this contribution once again is inversely proportional to Dampolan number. So for high Dampolan number, I can actually ignore that contribution. You you also have the delta function corresponding to reactance C equal to 0. You have another delta function at C equal to 1. Okay. Now, if I consider my density is only a function of reaction progress variable based on the property of PDF, probability density function, I can actually use this one, and that can lead to this relation where rho 0 is the unburned gas density. Tau is here not a time constant, but it's the heat release parameter which I mentioned earlier. It is essentially adiabatic flame temperature minus unburned gas temperature divided by the unburned gas temperature. Alternatively, you can consider it is the ratio of unburned gas density to the burned gas density minus 1. You will understand it immediately. So, for mean density, it is given by this rho 0 1 plus tau times C tilde. Come to this one basically from ideal gas law under constant pressure. So if I consider combustion is taking place under constant pressure, then you get this. Now, using the presumed bimodal PDF, you will have a contribution only from the unburned gas. At the unburned gas C equal to 0, so you get rho 0 multiplied by the weight at the unburned gas. At the burned gas, by definition of tau, burned gas density is rho 0 divided by 1 plus tau. As I said, 1 plus tau gives you the ratio between unburned gas density and burned gas density. Clear?
If you look to the previous slide, right, plane front is showing like this, and then you are taking a sampling line to each term, that term, the last term. So some portion is 0 and some reaction has not started yet, and some portion reaction is already started and there is some concentration of the.
This is that basically this line which is between C equal to 0 and C equal to 1, but the probability will be much.
As far as suppose you are physically looking at the line.
If I am physically looking at the line, this part is already in products, so that will give you this samples corresponding to this. If it is in this region, it is completely in the reactant, so I am going to see just C equal to 0.
And that value, the intermediate value that you are getting in which?
From this part, this intersection, from the flame crossings. Okay? This is the normalization part of the PDF. If I integrate the PDF, it should give you 1, right? That's how the PDF is constructed. So you have got two unknowns, alpha C, beta C. You have now two equations, this one, this one. If you actually ignore this part, consider that to be 0, based on that, you can get the expressions for alpha C and beta C as the weights of that picture. Clear? Now, this one is density weighted variance, isn't it? By definition, it is rho times C minus C tilde square, based on the Febvre decomposition, times probability density function of C, dC. What you get for the delta function at C equal to 0, the value of this was is going to be rho 0, unburned gas density. Here put C equal to 0, that gives you rho 0 C tilde square. Clear? For the burned gas, this one beta C, that's the weight for the delta function at the burned gas. Density is rho 0 divided by 1 plus tau, comes from the definition of tau, as I said. This one, for the delta function at C equal to 1, effectively this becomes 1, so you have 1 minus C tilde square. Clear? And I'm going to now ignore this bit, considering this is high dipole number. If you now put the values of alpha c and beta c here, you will end up with this expression. This is extremely, extremely important. Why it is extremely important? If this contribution is negligible, at very high dipole number, this one goes to 0, right? Then variance becomes C tilde times 1 minus C tilde. Earlier today we talked about a quantity called segregation factor. I told that basically gives you how it basically characterizes the extent of mixing. And I told when segregation factor is equal to 1, it's not mixed. If segregation factor is 0, then it's completely mixed. So if I divide both sides by C tilde minus 1 minus C tilde, you can see this side will become the segregation factor, this side becomes 1. And then there will be some contribution here. This is why this is the maximum possible value of scalar variance. Essentially, this contribution will be somewhere some negative value. In reality, this quantity scalar variance will always be smaller than this, because we are seeing the maximum value. Why two delta functions are giving me? They are completely segregated from each other. Anything in between will give a smaller value of scalar variance. Clear? What really happens? This is C tilde times 1 minus C tilde. This line, okay, the black line, and these are essentially the values of C variance for different flames subjected to different buoyancy effects. That's not important for the time being. I'm showing that the C tilde times 1 minus C tilde will have a parabolic profile with the maximum values at C tilde equal to 0.5. The maximum value for variance is going to be 0.5 times 1 minus 0.5, 0.25. But you can see from the GNS results, at the dipole number 1, variances are smaller than C tilde times 1 minus C tilde. Okay? If I look at the actual how the PDF looks like from direct numerical simulation, does it look like bimodal PDF? Bimodal means you will have a peak at C equal to 0, you will have a peak at C equal to 1. That's not the case, right? There's a considerable probability of finding values between C0 and C1. That means this contribution plays an important role, and that's why we are seeing a departure of the variance from C tilde times 1 minus C tilde. Here, as a result, very often this quantity variance cannot be closed using an algebraic closure. What I mean by algebraic closure, this equal to this cannot be invoked for general coefficient, because then you can incur significant, essentially, errors, as you can see. And we are showing here for different group numbers, but for a given dipole number. But if you consider smaller value of dipole number, as the dipole number decreases, the departure increases. I don't think you will be able to read with this resolution, but I will mainly tell you what happens. G star effectively is some kind of inverse of truth number. So think about a body force in the direction where you have, it is going from unburned gas to the burned gas. Unburned gas is heavier liquid, heavier fluid, and burned gas is lighter fluid. A heavier fluid cannot sit on top of a lighter fluid. So that gives rise to Dirichlet type of instabilities. So the positive value is that kind of situation. Negative value means the body force is directed from the burned gas to the unburned gas. Now lighter fluid is sitting on top of heavier fluid, which is a stable stratification. So this is stable stratification, this is unstable stratification, this one in the absence of any body force. What I want to actually mainly talk about, probably cannot see, but this pink line is equal, is the T3 term, which is essentially the reaction rate term. And here there is a green line, which we are not seeing here, but we should be able to see in the notes. That is the scalar dissipation rate contribution. Irrespective of what condition I am looking at, that the leading order balance is maintained by the reaction rate term, which is positive, generates scalar fluctuation. Scalar dissipation rate contribution is always negative because of the negative sign in front of it. It tries to actually kill the scalar fluctuation. And the leading order balance is maintained between those two terms in all cases, irrespective of which way my body force works or if there is no body force. It doesn't matter. Qualitatively, picture remains exactly the same. This term T3 mostly works as a positive term, that means a source term. It becomes slightly negative towards the burn gas side. I've shown it for two turbulence intensities. You will see there's a considerable difference in the magnitude of the terms as a result of the presence of the body force. Here it does not. The explanation is given here. Effectively, you can show that inertial force effects dominate at high turbulence intensities. Body force effects really don't play a very important role. Okay, that's why you are not seeing any significant difference in the behavior. But that's not really very important for our discussion. So now, clearly, let's take our stock first. We have shown that one can come up with an analytical expression, algebraic expression for scalar variance based on some kind of model PDF, but that analytical relation does not work unless you go for extremely high dipole number. So the only thing I can actually do is solve a model transport equation. If I have to do that, I have to model the unclosed terms in the scalar variance transport equation. And that's where we are going to focus right now. So first I'll start with the turbulent transport, which is given by this. Okay? So as you can clearly see, just looking at this term, the modeling actually depends on this quantity. If I can actually evaluate this quantity, I can evaluate the rest. Right? So, based on the Bray-Moss-Levy expressions of alpha C, beta C, you remember those things which we talked about rates before? And we can start with that presumed joint PDF of velocity and reaction progress variable. I can come up with this expression for mean, every mean values of velocity components. UIR, UIP are conditional mean values of velocity in unbound reactants and fully bound products. Okay? And you can see C tilde, the reaction progress, temporary average reaction progress variable, almost acts as a bridging variable between them. Clear? If I look at U prime, C prime, that's basically turbulent scalar flux, it gives you this relation. Ui prime is Ui minus Ui tilde, C double prime is C minus C tilde, and then I'm basically integrating it, gives me this. I think it is worthwhile to actually spend a little bit more time on that. This is for ith component, right? So let's put I equal to 1. So let's consider only x direction. Rho bar is a positive, right? Mean density. C tilde times 1 minus C tilde is going to be a positive quantity. Happy with that? According to gradient hypothesis, this one should be negative of rho bar times turbulent diffusivity del C tilde del x. According to the gradient hypothesis, just to follow, we discussed it already. Clear? If I consider my flame is such that this is my C tilde profile, and this is, what can you infer about del C tilde del x one, positive or negative? Positive, right? So then what will be the value for this one? Is it going to be positive or negative? Negative, right? Because this cannot be negative, eddy viscosity cannot be negative. Clear? Now let us look at the functional form. If the conditional mean value of velocity in the product is greater than conditional mean value of velocity reactants, then this is going to be a positive term. Gradient hypothesis tells me it has to be negative, but it will give me a positive value, and that will lead to counter gradient transfer. We'll come back to that later in the following lecture tomorrow. If it is negative, obviously I am seeing the expected behavior. And this is one of the major issues in terms of closing turbulent scalar flux in reacting flows. For premixed flame, partially premixed flame, and there are evidence says in the case of non-premixed flames that you might actually get counter gradient transfer. If you have a laminar flame, that means I'm not talking about really laminar flame, but weakly turbulent, so that I can get some analogy from almost a laminar flame. Okay? Most of you probably have done some more courses on compressible fluids, I'm assuming. So think about this. Here, this is the flame, it is moving in this direction. So here you will get something like this. Sub velocity, unburned gas from the mass balance, it will be right? You must have done this kind of thing for normal shock, similar kind of things. Yeah? Density drops across the plane. What has to happen for velocity? Velocity increases. If velocity increases, this one is greater than this, you are going to get counter gradient. Here? Now, in the same method, if you, instead of having C minus C tilde, if you have C minus C tilde square as it is shown, you will end up with the analytical relation like this, which is also a function of turbulent scalar flux. So, effectively tells me if this one shows counter gradient behavior, I might actually expect counter gradient behavior here. If it shows gradient behavior, I will actually expect gradient behavior. And based on that, let's say gradient hypothesis, this is what people generally use. And this is a model which effectively we came up with. The idea is such where S is the segregation factor. If the segregation factor goes to 1, which happens at very, very high dipolar number limit, then this expression boils down to this expression. And first important thing, if you look at, DNS is the black line, and if I use gradient hypothesis, you get this line, faint line. You can clearly see how gradient hypothesis does. It does not capture the behavior at all. Okay? If I now consider this expression and I extract the scalar flux directly from direct numerical simulation data, you can see the agreement between this black line and this brown line is quite good, at least in comparison to gradient hypothesis. Okay? But this quantity, scalar flux, is itself an unclosed term. So I need model for that. We came up with a model which can handle both gradient and counter gradient transport, and once you plug that expression there, it still continues to do a good job. Obviously, there will be some variation between the when I'm taking true value of the scalar flux from DNS and when I'm modeling it. Okay. We talked about this, so I'm going to skip this one. This is essentially the dissipative action. So, how the reaction rate is related to scalar dissipation rate. So, on averaging, you get this. Let me clarify this sentence. Maybe in the updated slide I will actually change it. I'm telling on not really Febvre averaging in a literal sense, on using the Febvre decomposition and then the averaging, that will be this equation. Usually people neglect the molecular diffusion contribution because that term is really, really small in comparison to turbulent transport. So, based on this equation, you can come up with this equation for C tilde times 1 minus C tilde. For the strict flame limit, that means at very high dipolar number, if I actually equate this and equate this, then for very, very high Reynolds number, ultimately you end up with this, and then once you replace the scalar flux of variance using this, ultimately you end up with this result. So if you use 3 minus 2 for very, very high Dampoler number, ultimately it boils down to this. And that effectively gives you ultimately this relation. Where Cm effectively is a thermophysical constant evaluated from laminar premix flame values. So this is a thermophysical constant. Once you know your mixture based on the laminar flame, you can evaluate that. For a given mixture, this is constant. So it's a mixture specific constant. This is the mean reaction rate, rho bar density, mean density, scalar dissipation rate. So effectively, mean reaction rate in premix flame is directly proportional to scalar dissipation rate. So you need scalar dissipation rate not only for representing the molecular dissipation contribution, you may need that even for closure of mean reaction rate. Obviously, for passive scalar mixing, this aspect does not hold. You need it anyway for representing the dissipative action. Clear? What I showed so far is valid for high Dampoler number flames, but if one does scaling analysis, one can show this expression actually remains valid in a scaling sense. So instead of having equal to sign, you can put roughly a scaling sign, and then it remains valid even for low Dampoler number condition up to a certain extent. So this is one way to actually represent the mean reaction rate. You might remember, I think it was yesterday when I probably talked about mean reaction rate closure. I told there is no straightforward way to actually approach it because reaction rate is a highly nonlinear function of temperature and the species mass fractions. So this is one thing, one way of doing it. But before I go any further, NC tilde is this quantity, and epsilon C tilde is the fluctuating part of NC tilde. In rands, the average contribution is often negligible in comparison to this, so very often, essentially, equality is considered between these two. We already did a tutorial problem between this one and this one, so you might remember that. There is another way to do it, the modeling of the mean reaction rate, which is by a quantity which is commonly referred to as flame surface density. Physically, it represents flame surface area to volume ratio. Now, reaction rate effectively is the burning rate per unit volume. Okay? So if I consider, I know somehow for the time being that flame surface area to volume ratio, and if I assume per unit surface area, my burning rate is similar to a laminar premix flame, then I can multiply that with the surface area to volume ratio to get this one, mean reaction rate. That's the idea. It is essentially some kind of surface specific average of density weighted displacement speed. Just for your understanding, displacement speed is the speed with which the flame, premix flame, moves normal to itself with respect to the background fluid motion. Okay? So whether you use flame surface density, which is defined as this, or scalar dissipation rate, just from mathematical definitions, you can see you will need the information of the magnitude of the gradient of the scalar anyway. They are closely related, scalar dissipation rate and flame surface density. You might remember in the first tutorial, we actually ended up getting a transport equation for this one. Clear? Now, let's see how it works. So for T3, using all of those, essentially this is the term which one can actually simplify based on the flamelet assumption. Flamelet assumption means I am telling turbulent flame locally has quasi-laminar properties. Okay. So if you look at DNS and this one, they are inseparable. So this simplification is possible. But please note this term, mean reaction rate term, is an unclosed term. In actual RAN simulation, I need to put a model there. Okay. If I put this for Froude number, large values of Froude number, you don't see any major difference. For low Froude number and low turbulence intensity, it slightly over predicts. If I use epsilon C tilde, it slightly under predicts at low turbulence intensity, low Froude number, negative value of Froude number. Negative value of, basically negative value of G star means stable stratification. So essentially, the model works for highly turbulent condition. If G star is negative, that means there's a stable stratification. It tries to kill turbulence. It basically tries to relaminarize them. Okay? When the turbulence effects are weak, then there are some variations for higher turbulence intensities, where turbulence effects are strong, works pretty well. Now, scalar dissipation rate closure. You have two options: algebraic closure, or you actually go for a transport equation based closure. We talked about this idea before, okay? And both are valid for RANs and LES, but this is specific to LES. You cannot do this for RANs. We talked about the idea of dynamic modeling yesterday in the context of subgrid stress closure. Effectively, the model parameters you are actually capturing based on the local flow properties, in contrast to specifying some value a priori. Now, this is a horrible looking equation. This is the full transport equation for scalar dissipation rate. Now, it might look horrible, but the physics is beautiful in my opinion. Transient term, mean attraction term, molecular diffusion. This is a little bit strange to say, dissipation rate of scalar dissipation rate. Okay? The molecular dissipation of dissipation rate. So subgrid convection, basically nothing but turbulent transport. This is density variation because you see you have a density gradient. If I'm dealing with incompressible fluid, whole term disappears. This is called scalar turbulence interaction term. How turbulence training interacts with the scalar gradients. And the behavior essentially is determined by this term. This is the reaction rate contribution, and this is the contribution because of the variation due to species diffusivity. Okay? It's a horrible looking equation, I know, but all the necessary physics is there. And it has effectively a lot of unclosed terms. T1 is unclosed, T2 is unclosed, T3, all three components of T3 are unclosed. This is unclosed, this is unclosed, and this term is also unclosed. So you need to have model for each one of them. Vishnu asked me in the recess that whether scalar dissipation rate affects turbulence or turbulence affects scalar dissipation rate. In a non-reacting flow, scalar dissipation rate does not directly affect turbulence. Turbulence whether it's a reacting flow or non-reacting flow affects scalar dissipation rate. You can clearly see turbulence training effects, velocity gradient effects are explicitly there in the scalar dissipation rate transport equation, and that's how the turbulence effects are coming into the evolution of scalar dissipation. This is how those terms behave for high damp Coulomb number and low damp Coulomb number situation. D4 is the reaction rate term, minus D2 is the dissipation rate term. So these two are the leading order terms, the reaction rate term and the molecular dissipation term. For high damp Coulomb number conditions, the term arising because of density variation plays a very, very important role. It is not zero, still plays somewhat important role. D3 here works like a sink term because it's negative. Now, if you look carefully for T3, that is the scalar turbulence interaction term where the strain rate effects are coming into the scalar dissipation rate evolution, starts as a positive term, then becomes negative. Okay? T1 does not play very important role. It's not a leading order term. So, if there are modeling inaccuracies in T1, it doesn't significantly affect the overall accuracy. Clear? But the major difference lies in the behavior of T3. It changes sign completely. If you look at the scalar flux of the scalar dissipation rate and effectively following the same analogy, if I look at the gradient of scalar dissipation rate, you will see they are of the similar sign, at least for case A, for this one, the solid line. You will see mostly same sign. So scalar flux of scalar dissipation rate also can show counter gradient behavior. Case B corresponds to a higher turbulence intensity, lower damp Coulomb number. It shows mostly gradient type of behavior. The zero value is shown here. Okay. So, if I take product of this scalar flux times del C tilde del x, if it is positive, then it's a counter gradient transport. If it is negative, gradient type of transport. So, you can see for case A in the solid line, we see counter gradient transport, and the case B we see gradient type of transport. From where it comes, if you look at this, if I now multiply that with del C tilde del x, 1, this will be positive, this will be positive, this terms are positive. So if it is a gradient type of transport, this product will always be negative. Clear? So we modeled the scalar flux of scalar dissipation rate as a function of turbulent scalar flux, because when the turbulent scalar flux becomes counter gradient, this one also becomes counter gradient. And you can see it does quite a good job in terms of capturing the behavior, at least better than the gradient hypothesis. Based on some scaling argument, the T2, the density variation term, is modeled in this form. We talked about something called Karlov's number. Just to remind you, it gives you the measure of chemical time scale to Kolmogorov time scale. If Karlov's number is much, much larger than 1, essentially, At least in principle, you are going from the reacting to non-reacting unit. So the functional form is such that when Carlovis number is large, T2 strength will go down. Why? At high values of Carlovis number, it tends towards the non-reacting situation. If non-reacting situation prevails, your density gradient effects are going to be weak. That's what the model essentially tries to represent. As you can see, it does reasonably good job. Now, T3 term, you remember this T3 term change sign? This has three components. This one coming because of the mean scalar gradient. T32, everything is fluctuating part. T33 comes from the mean velocity gradient. But if you look carefully, they are dependent on the alignment between the reaction progress variable gradient with local strain rate. Just for your information's sake, this term appears slightly different manner in the plane surface density transport as well. So you cannot get away with it, and it is dictated by effectively in this manner where E alpha, E beta, E gamma are the eigenvalues of the strain rate tensor. This is the most extensive principal strain rate. That means most positive eigenvalue. Here, E beta is the intermediate one. E gamma is the most compressive principal strain rate. That is most negative. Okay? We have angles, theta alpha, theta beta, theta gamma. These are the angles. Gradient of C, gradient of scalar makes with the eigenvectors corresponding to these three eigenvalues. Here, now if you spend a little bit of time looking at the expression, eigen system is mutually perpendicular. So if my scalar gradient aligns with the most extensive principal eigendirection, then this cos square theta alpha is going to be 1. Here, this will be 0 because of mutually perpendicular thing, cos theta beta is going to be cos 90 degrees, cos square 90 degree. Cos square 90 degree, you know what the value is going to be. Similarly, cos square 90 degree for theta gamma as well. So these two will not play any role. I told this one is the most extensive principal strain rate. You have a negative sign in front of it. It will give you a negative value of T3. Right? Clear? Happy with that? If it aligns with the most compressive principal strain rate, then this contribution is going to be 0 because it's going to be cos square 90 degree. This will be cos square 90 degree. This will be cos square 0 or 180 degree. Doesn't matter. If I have a preferentially linear alignment, that's going to be 1. So that this is most compressive principal strain rate. That means it's a negative. I have a negative sign. Makes it what? Positive. So the sign of T3 essentially is determined. Now probably you can appreciate why it depends on the relative alignment of scalar gradient and the strain rate eigenvectors. Clear? Let's look at the probability density functions of these angles. This is PDF of cos theta alpha. For high dipole number case, you can see T is at 1. So basically showing predominant alignment with the most extensive principal eigenvector. Clear? recall if it is aligning with this, then these contributions are 0, you are going to get T3 to be negative. That's what we got in that case. What happens? I have shown these lines for different values of C. C equal to 0.1 means in the unburned gas side. That means chemical reaction has not happened yet. We are in the preheat zone. We are coming close to reaction zone 0.7 to 0.9. 0.7 is close to the reaction zone. 0.9 again we are going to the burned gas side. If you look carefully towards the unburned gas side when chemical reactions start, the alignment is predominantly with 90 degrees. That means the peak is at cos theta alpha 0. As you come towards the reaction zone where the heat release effects are strong, it starts to become positive. Alignment with the positive. Here, so this is what I have already said. These are basically the take-home messages, and essentially just the opposite thing you are going to see when you are looking at the alignment with the most compressive principal strain rate. For high damp Coulomb number case, no alignment with the most compressive principal strain rate, or it's basically perpendicular to the most compressive principal strain rate because that's where the peak of the PDF is. And you can see in the case of low damp Coulomb number case, scalar gradient predominantly aligns with the most compressive principal strain rate. As I told, if damp Coulomb number decreases, you are going from the reactive region to the non-reactive side. So in passive scalar mixing, you see this behavior. In the case of passive scalar mixing, without chemical reaction, scalar gradient preferentially aligns with the most compressive principal strain rate. I already told that if you have predominant alignment with the most compressive principal strain rate, effective 83, this term will be positive. Okay? That means under turbulence, scalar gradient is generated. But under reactive condition, when predominant alignment with the most extensive principal strain rate eigendirection is obtained, instead of generating scalar gradient, it actually kills scalar gradient. So what I have told, that's basically shown schematically here. Think about this. If scalar gradient can actually be written in a normalized form as flame normal. If flame normal aligns with the most compressive principal strain rate, two isoscalar lines are coming close to each other. What will happen if they come close to each other? Scalar gradient will go up, right? In the case of alignment with most extensive principal strain rate, two isoscalar lines are going far from each other, scalar gradient drops. Physically makes perfect sense. Essentially, it is a matter of competition between the strain rate induced by thermal expansion, which scales with tau, that I mentioned earlier, which is ratio of unburned gas density to burned gas density -1. It is also dependent on Lewis number. As Lewis number drops, that effect becomes stronger, and the chemical strain rate given by laminar burning velocity and the flame thickness. So when this one wins over turbulent straining, then it happens. When turbulent straining, which is basically given by U prime over L, that wins over this, you will end up with this one. So these two effects can be actually shown in this way. So for small values of damp Coulomb number, you are going to see this. For large values of damp Coulomb number, you are going to see. So this physics was not accounted for in this model. If you look carefully, this model has no mechanism by which negative values of T32 can be predicted. It is always possible. We came up with this model in 2007. We refined it further with time, but let's see. So this was originally proposed for premix flames as well as for passive scalar mixing. And our thing is for both conditions. So firstly, T31, you can see CS model is the refined model where the scalar gradient alignment effects are considered, and that does a relatively good job in terms of capturing the behavior of T3. Whereas the previous model continues to give only a positive contribution. The prediction of the earlier model remains reasonable. Our model probably does a little bit better job. Here you see the major difference. Once again, the previous model just predicted a positive value, could not capture the transition. The revised model can. Effectively, people nowadays use our model as a standard model because of that. This one. And similarly, it shows the behavior of T33. I think apart from making the model more accurate, both models do reasonably good job. T4 minus T2 are generally modeled together as a complete dissipation effect, because please note, we wanted to actually come up with a model which can be valid both under reacting condition as well as non-reacting condition. Under non-reacting condition, T4 is the reaction contribution that will be zero. So that's why the model is given in such a form that it has a negative sign in front of it. One can do a realizability analysis. Realizability analysis in this context means scalar dissipation rate cannot be negative. And that basically ensures that this beta 2 value has to be greater than this. You can do an analysis based on ordinary differential equation and then can come up with this relation. And you can see it is not perfect, but in Rand sense, if you get this level of increment, you should be happy. Now, let us see what impact it has. This is the mean reaction rate, as you know. We already showed that this one is the scalar dissipation based reaction progress variable. And this is the flame surface density based closure under certain assumption. Sigma gen, once again, is the flame surface density, which gives you the measure of flame surface area to volume ratio. If you look carefully for different Lewis number, this one is like stoichiometric methane airplane. This one is 20% methane by volume blended with methane. That's right. Hydrogen, 20% hydrogen by volume blended with methane. This is 40% hydrogen blended with methane. This is lean hydrogen blend. Okay? If you see this one, the second one, that model does reasonably good job when the Lewis number is of the order of unity. So mainly for hydrocarbon flames. And this one probably is ethylene air flame, where Lewis number is greater than 1. This one actually does quite a good job for different ranges of Lewis number, different values of Lewis number. without any modification. And that gives this as a good option for reaction rate closure. Equipped by that, one can do a scaling analysis and then effectively come up with a correction for this term like this, and then it starts to do a reasonably good job, but still there are some underpredictions. This is important because essentially we are moving from hydrocarbon fuel to hydrogen-based fuels, and essentially an accurate closure for reaction rate is needed if we are going for a hydrogen-based economy in the future. Similarly, Lewis number plays a very important role. Subsequently, Lewis number effects are taken into account. If you consider the original model that I showed without any Lewis number correction, for very small Lewis number, it doesn't work. But we have modified things where Lewis number effects are explicitly taken into account. Lewis number also changes the relative alignment of scalar gradient with principal strain rates. As Lewis number decreases, because of thermodiffusive effects, the chemical straining effect becomes strong, increasingly strong with decreasing Lewis number. So you will see the alignment with the most extensive principal eigendirection is much, much larger here in comparison to Lewis number 1 from the PDFs. And just the opposite thing you are going to see here, that for smaller values of Lewis number, the predominant alignment, apart from towards the unburned gas, there is no heat release effect. Everything is not really aligning with the most compressive principal strain rate eigendirection, whereas in Lewis number 1 condition is principally aligning with the most compressive eigendirection. And that will always be having an impact on the behavior of T32 term, where the Lewis number variation is taken into account. I already showed this model, MB model, which is Nath and Bhowmik model, which was the originally proposed model. Does not capture the behavior, it continues to predict positive value. This was our earlier model. Does a relatively good job in the context of unity Lewis number, but when you go for Lewis number 0.34, it doesn't work, and that's why it needed some modification. And that basically does a reasonably good job. I'm telling it's quite an old thing, which was done in 2009, so it's no longer that new a model. People are already using it in the literature. Effectively, the model looks like this. So this part, the first part, effectively takes care of the turbulent straining effect. Basically, this represents the generation of scalar gradient because of the preferential alignment of scalar gradient with the most compressive principal strain rate. Two isoscalar lines are brought closer to each other. Okay? One with negative sign, this part, this takes care of essentially the chemical straining effect because of thermal expansion. Isoscalar lines are going far from each other. If they go far from each other, scalar gradient drops. And the competition between these two essentially determines how T32 is going to behave. Now, we have got all the terms modeled for scalar distribution rate transport equation. If I carry out an order of magnitude analysis and basically find which terms are most important terms for high Dampoler number case. And based on that, we basically came up with an equilibrium condition when generation rate of scalar dissipation rate is in equilibrium with the destruction rate of scalar dissipation. And by this condition, we put the individual model expressions for these terms, and that gave us an algebraic expression for scalar dissipation rate. Okay? Now, The solid line is the DNS data. There are various models, but this model, this Pola model, is this one. Effectively, you will see that the classic model, which is basically the linear relaxation model which I showed earlier today, needed to be divided by a factor of 8. That model essentially predicts an order of magnitude higher value than what is obtained from DNS data. Whereas this one does quite a good job in terms of capturing the behavior for high dipolar number and relatively moderate values of dipolar number partitions. We extended it for non-unity Lewis number, and as you can see, it's not perfect, but it is much better than anything else available in the literature. Now, this expression remains valid, we showed in the context of RAS. Does it remain valid in the context of LES? Please remember, originally this expression was derived for bimodal PDF. Now, if I look at a Febvre filtered value of C equal to 0.5 and look at the PDFs for different filter width, filtering, please remember, is a convolution operation. So it's a smudging operation. Okay? So for small filter width, essentially you get a delta function kind of thing. So at C tilde equal to 0.5, you will get only the samples of C equal to 0.5. A small filter width, because small filter width means you are going to the DNS limit. As you go for larger filter width, the probability of finding C not equal to C tilde increases. Okay? So as you can see, if I define a subgrid dipolar number like this, where this U prime delta is estimated based on the subgrid kinetic energy, it increases with increasing filter width. And we actually extended the RANS model in this manner, where these are essentially bridging functions. This is a function which such that effectively when we put the values of C, T and rho, you get the actual reaction rate. It's basically the functional form in the instantaneous sense. The idea is when filter width is much greater than the flame thickness, then this term goes to 0. This term becomes 1, so that is multiplied with this. When filter width goes to 0, that means DNS limit, then exponential of 0 is 1, 1 minus 1, this term is switched off, basically it goes to that. Let's see. You can see with that correction, even in LES, for different conditions, different turbulence intensities, different heat release parameter, the model does relatively good job. There are various ways to actually model. One is this way. Sometimes it's called an alternative wrinkling factor, because if the value is in the laminar case, the value is going to be 1 as this parameter goes away from 1 because more subgrid wrinkling has taken place. Very often people actually model it using some kind of a power law. And this one is called inner cutoff scale. So using this relation, one can actually come up with this. So if somebody actually plots this one as a function of log delta, the slope of the line gives you the power law exponent. So firstly, see whether it actually actually gives you a power law or not. There's a part which is linear, so the slope will give you the power law exponent, where this linear part actually intersects this axis. This part gives you the normalized inner cutoff scale. And based on that, one can come up with this relation. So this can be a potential model. One is this model. This is the model people generally use for passive scalar mixing. And this is the model which I showed algebraic closure earlier, but now it is extended in such a manner. Here I have a bridging function once again. The idea of bridging function is that when the flow, when the filter width is such that delta is very small, so if you put delta equal to 0, this term goes to 0. Okay? In the DNS limit, C tilde becomes C. D tilde becomes D. So NC becomes same as this one. Okay? That's what happens in the DNS limit. When you go for very large value of delta, basically that you are converging from LES towards the RANS side. For large values of delta, exponential of minus infinity goes to 0, right? So you will have 1. So with that, you will have this contribution coming in. It comes from, once again, the equilibrium of basically these terms. Essentially, I am not going to go through this because we have already talked about that, how these terms can be modeled. And similar thing is done from the point of view of LES. You can see the equilibrium is maintained between the terms arising from density gradient, turbulent straining, chemical reaction. This is because of the diffusivity gradient, the combined contribution, and this is the molecular dissipation contribution. They roughly are in equilibrium. So I can actually invoke that to justify why I am actually putting this expression here, because this expression was originally derived based on the leading order balance of the terms in the scalar dissipation rate transport equation. If we look at the volume average behaviors of scalar dissipation rate and compare that with GIAN data, first important thing to see that power law exponent slope increases. In other words, as turbulence intensity increases, the linking gets increased. Nothing surprising, you would expect that physically. When I'm not even modeling that, I'm taking the value which I am getting from the DNS data and I'm putting in the power law model. It actually captures, so there are no surprises there. I am just putting that value and it should do the job. Conventional model, this one, doesn't capture the behavior at all. Okay? The new one, which we did based on the equilibrium of the generation and destruction of scalar dissipation rate, that's a very good job in terms of capturing the behavior. And same for non-unity Lewis number, you will see that the power law exponent increases with decreasing Lewis number, basically telling that as Lewis number decreases, plane becomes more wrinkled because of the thermodiffusive effects. So, how is the local behavior? This is for very small filter width. Delta equal to 0.8 delta thermal, and this one is for large filter width, relatively large filter width. You can see, even for the values which are extracted from GNS data, if I put in power law model, it does not capture the local behavior at all. Although it captured the volume average behavior, it doesn't capture the local behavior at all. Conventional model did a horrible job before in terms of capturing the volume average behavior. It doesn't look that bad, but it's posed quite a bit of underprediction. New model actually does a reasonably good job for different turbulence intensities. In fact, if something to be noted, it does a better job as turbulence intensity increases. It's not so new model, it's proposed in 2014. It's no longer that new. Before I leave this slide, just mention one thing. The physical reason why power law model does not actually do a good job in terms of capturing the local behavior. Although I took all the values directly from DNS data, and so that it actually captures the volume average behavior quite well, because scalar dissipation rate is a quantity which shows multi-fractal behavior. So one power law exponent is not sufficient to actually represent the scalar dissipation rate. Okay? If you capture the local behavior, the volume average behavior gets messed up. If you actually capture the volume average behavior with a single exponent, the local behavior gets messed up. Okay? Non-unity Lewis number, it's not perfect. But if you look at the blue line in comparison to green line or red line, I think probably one can live with that. Okay. Nothing better exists at this point of time. Now, I told the model needs to be actually implemented to see whether it actually does a good job. So this is a configuration like a backward facing state. It's called Oracle's Barman. Unfortunately, in this one, there is only velocity measurements. And you can see effectively, this is an alternative model, experimental data. The model actually does quite a good job in terms of capturing velocity behavior. This is a blob body stabilized flame. This one is a blob body, flow is coming from this side. Again, in terms of the mean velocity, fluctuating velocity, it does a very good job. And similarly, this one has a temperature, it actually does a good job in terms of predicting the temperature as well. These are by 3 different models. But please see, it may not, at some places, the predictions might look like comparable, but instantaneous behavior is quite different. And so, boundary condition, numerical setup, grid size, everything are the same. Everything is kept identical here. The only thing is model is different, and you can see how the flow structure changed. In this case, you see kind of puffing around the blob body. Here you see vortex trail. We actually use that for a swirl flow, which is a generic gas turbine combustor. This is the isothermal simulation, the vorticity magnitude, and this side is the reactive flow simulation. And you can see it's very different. In this case, you will have a precessing vortex core which basically moves like this. That is completely gone here. Okay? Predictions. I think reasonable predictions of axial mean velocity, mean temperature, RMS temperature as well. Now, let's go for dynamic modeling. basically the hat is called test filter. Using this identity, I can come up with this kind of expression finally for beta c parameter, a model parameter. As you can see, I have not given any value for beta c. It is actually determined by this function at different situations. And you can see it does reasonably good job. Once again, if anything, at higher turbulence intensity, the model behavior becomes better. And previously you saw the static model constants. That means when you predetermine model constants were specified, it showed some over predictions. Now the agreement is much better. Same for non-unity Lewis number. Here there was quite a bit of over prediction. It's not perfect, but it's not that bad either. This side, this is a kind of a jet flame, Bunsen methane flame. This side with the static version of the model with static model coefficients. This is in the dynamic model with 1.5 million grid points. You can see corresponding predictions. Solid line is for force grid, dotted line for finite grid. Now, just as I showed before, one can extend the modeling methodology for RANs for alias perspective as well. Basically, all the concepts were borrowed from the RANs modeling. The subgrid flux is modeled in such a manner that this part is the gradient part, this part is counter gradient part, depending upon the relative strength, whether you are going to get gradient effect or counter gradient effect. As you can see, the model does a reasonably good job in terms of capturing DNS. Similarly, for different values of Lewis number, density variation term, the whole idea borrowed from RANs, nothing else. Again, you can see not perfect, but not very bad as well as a first attempt. Works reasonably well for different Lewis number. Scalar turbulence interaction term, where we talked about the importance of the alignment of scalar gradient with the principal strain rates. Same concept is taken into account. Once again, you can see this part essentially the positive part accounts for the relative alignment with the most compressive principal strain rate, so isoscalar lines are coming close to each other. This one, alignment with the most extensive principal strain rate, isoscalar lines are going farther away from each other. See, it shows here in small turbulence intensity is negative value, and then at high turbulence intensity starts as a positive transmission. It captures the transition quite well. Same for different Lewis number. Once again, the idea just for recapitulation purpose. So this part effectively is this one, which basically means that when we are actually having predominant alignment with the most extensive principal strain rate, the isoscalar lines are pulled apart. This part effectively is this situation where scalar gradient aligns with the most compressive principal strain rate, isoscalar lines are coming close. T4 minus T2 plus the diffusivity variation term. Again, it is modeled as this, so that effectively you will have a negative contribution because T4 goes to 0 under non-reactive flows. Again, you can see it captures the behavior quite well. And similar thing for non-unity Lewis number. So effectively, we looked at scalar transport, the transport behavior of scalar variance and scalar distribution rate transport equations. We have given the physical explanations for the behavior, statistical behaviors of different terms. You can see scalar dissipation rate can be used for the closure of mean or filtered reaction rate in addition to the modeling of the micro-mixing process. The situation that I showed for high values of Karlov's number or low values of Damkohler number is qualitatively similar to the non-reacting situation. So the statistical behavior of scalar dissipation rate in reacting flows can be significantly different to non-reacting flows, and your model should be such that it can capture both behaviors equally well. With that, I'll stop.